All right, today we are diving deep into one of the most intense, most high-stakes processes in all of manufacturing. I'm talking about quenching steel. It's this wild place where incredibly precise science slams right into what looks like pure brute force. And it's all done to create materials with some truly amazing properties. So let's get into it and see how engineers even begin to control this chaos.
And you've got to understand the stakes could not be higher. On one side, you've got the prize, a perfectly formed, incredibly hard and strong part, maybe a gear that's about to go into a high-performance engine. But on the other side, you've got the risk, a warped, cracked, and totally useless piece of expensive metal. That line between success and total failure, it is razor thin, and it all gets decided in just a few violent seconds.
You know, to really get quenching, you have to think of heat treatment as a kind of modern-day alchemy for steel. You're taking a common material and turning it into something extraordinary. And within that whole process, quenching is, without a doubt, the most dramatic, the most violent, and the most crucial step. It's that one moment where all that potential becomes reality.
So, what exactly is it? Well, in simple terms, quenching is just the super rapid cooling of hot steel. But that incredible speed is the key. It traps the steel's internal crystal structure, locking it into a formation called martensite. Now, martensite is incredibly strong, but it's also highly stressed. So this speed, it's the secret to getting that amazing hardness. But, as you're about to see, it's also the root cause of pretty much all the problems.
Because that rapid cooling, it literally ignites a war inside the steel itself. You've got these two powerful, invisible forces that suddenly start fighting each other, and they're both fighting against the engineer's goal of making a perfect part. Understanding this internal battle is everything if you want to control the outcome.
Okay, so the first combatant in this war is something called thermal stress. The best way to think about it is to imagine pouring boiling water onto a frozen car windshield. That sudden, uneven temperature change can make it crack, right? Well, the exact same thing is happening here. The outside surface of the steel cools and shrinks almost instantly, while the core is still blazing hot and expanded. This huge mismatch pulls the surface into some really extreme tension.
And then there's the second combatant, transformation stress. And this is where it gets really wild. While the outside is rapidly cooling and trying to shrink, the crystal structure on the inside is actually morphing from its hot, flexible state, called austenite, into that super hard martensite. And get this, that transformation forces the steel to expand in volume. So you have a literal war going on. The outside is shrinking while the inside is trying to grow. This quote from the source material just sums it up perfectly. You get this chaotic cooperation and competition between shrinking and expanding forces. And what that creates is this fluctuating, totally unpredictable stress field deep inside the metal, which, as you can guess, can very easily lead to a catastrophic failure.
And if that internal war is lost, well, the consequences are pretty devastating. The part can bend, warp, and twist, completely ruining its shape. It can shrink or thicken in unpredictable ways, making it totally useless. And worst of all, it can develop what are called quench cracks. These are fatal flaws that instantly turn a valuable engineered component into a piece of scrap.
So the big question is, how do engineers possibly control this level of chaos? For decades, the answer has been to try and physically wrangle all these variables, using a mix of chemistry, timing, and sometimes just plain old brute force.
The first choice you have to make is the quenchant itself, the liquid you're plunging the steel into. Really severe quenchants like water or brine cool things down incredibly fast. That gives you maximum hardness, but it also means you're taking on the maximum risk. On the other hand, you've got milder quenchants like oil or special polymers. They cool things down slower, which reduces the stress, but they just can't get the job done for every type of steel. So it's this constant trade-off between performance and risk.
Now, this challenge led to some really clever techniques, like quenching, which you can see laid out here. Instead of just one violent plunge, the process is actually interrupted. First, you quench the part into a hot bath of, say, molten salt, and you pause it right about the temperature where that stressful expansion begins. Then you hold it there. This lets the temperature even out from the core all the way to the surface. It lets all that thermal stress relax before the transformation stress kicks in. It's brilliant. Then, and only then, you cool it slowly through that final phase.
And hey, when all that finesse and clever timing just doesn't work, there's always the brute force option, press quenching. And yeah, it's exactly what it sounds like. You literally clamp the part into a fixture or a press that physically holds it straight while it's being quenched. It's super effective, especially for long, thin parts that love to warp, but man is it expensive and slow.
These physical methods have taken us a really long way, but the real revolution, the real game changer is happening in the digital world.
The new goal isn't just to react to these forces anymore, but to actually predict them before they ever have a chance to happen.
And this brings us to a really crucial question, right? How can you possibly see an invisible war of stresses that's playing out inside a solid piece of steel, all in a fraction of a second?
Well, the answer is simulation. What's so incredible about a simulation like this one is that it makes the invisible visible. Using really complex physics models, engineers can run thousands of virtual quenches. These digital tests can predict exactly where those competing stresses are going to build up, showing them potential cracks or warping long before a single piece of real metal ever gets heated. But modeling this process, it is no small task. I mean, the physics involved are unbelievably complex. And as you make the simulation more and more accurate, the computing power you need doesn't just increase, it grows exponentially. It demands an absolutely massive amount of resources.
So this massive computational challenge is exactly where the next frontier of control comes in. We're now moving beyond just simple simulation, and we're putting artificial intelligence right in the hot seat.
AI and machine learning are completely transforming the field. By analyzing huge data sets from all the quenches that came before, they can predict the final properties of a part with incredible accuracy. This lets them optimize the process in real time, controlling the fluid flow, the cooling paths, and they can even predict when the equipment itself is going to need maintenance. The end result? Way less waste and a huge reduction in all that expensive, time-consuming trial and error.
And the impact is huge. We're talking about a potential reduction in physical experiments of up to 40%. Just think about that. By training machine learning models on both simulation data and real-world results, you can cut down the need for costly physical trials by almost half. That is a massive leap in efficiency, saving so much time and money.
So with all this incredible digital control, with AI in the mix, have we finally conquered the violent physics of quenching? Well, not exactly. And this brings us right back to a fundamental limit.
So, here's the crucial takeaway. At the end of the day, it doesn't matter how sophisticated our simulations are or how intelligent our algorithms get, they don't change the fundamental laws of physics. Thermal expansion is real. Phase transformations are real. What all this amazing technology does is give us a smarter, faster, and more powerful way to navigate those unyielding physical laws.
And that kind of leaves us with a final, lingering thought. We're in this constant race between our ability to control a process and the fundamental physics that govern it. So as our digital tools and our AI models get closer and closer to perfection, what new, more subtle challenges are we going to uncover buried deep within those unyielding laws of nature?